Good afternoon and welcome to this Wednesday afternoon's Data Core Labs webinar, Catching the Software-Defined Storage Wave. My name is Jeff Slapp. I'm with Data Core Software. Just a couple housekeeping tips before we begin. We're going to try to keep this session limited to about 20 minutes with some time afterwards for Q&A. And please feel free to ask questions in the question box that you'll find on the right-hand side of your GoToMeeting screen throughout the webinar, and we'll answer them as soon as we're done presenting. Okay. A little background information about me. I've been in the IT field for 17 years now. 15 of those years has been working specifically with virtualization technology, whether it be compute or storage virtualization. 10 of those years has been with Data Core Software in the field in some form or fashion. 5 years, the first 5 years of my experience working with Data Core has been as a partner, deploying solutions worldwide for them. And 5 years as a customer of Data Core for a South Florida cloud service provider. And now most recently working in the technical product marketing specialist role. So let's take a look at how storage has changed. It's changed, the landscape has changed significantly as of late. Starting back in the mid-'80s with very siloed software or storage-based frames, growing very quickly into a large array of flash-based, SSD-based, high-capacity, spinning disk, and everything in between. Cloud storage being the most recent one on the scene. And this is becoming extremely challenging to manage and maintain, especially as the demand for capacity and performance grows equally in the industry. A lot of incompatible devices out there. Software driving each one of those frames or those silos of storage specific from each manufacturer, and very challenging to manage all of those heterogeneous storage platforms in the environment. So what we're going to do is we're going to take a quick look at software-defined storage, what that means, and both from a a theoretical as well as a practical view, and how we can actually achieve some of the principles that we're going to go over here in this webinar today. So what is software-defined storage in a general sense? A couple key principles here. One, the idea around software-defined storage is that we want to leverage any commodity storage hardware platform. We really want to be able to take all those different makes and models out there and unify them in some way. We would also want to take that same software intelligence and run that on also commodity-based server hardware. Have the flexibility both at the compute layer where the intelligence is running as well as on the back end where the storage and where the data resides. Unify all these disparate storage technologies so that they can be essentially managed as a homogeneous storage platform, even though they're made up of many heterogeneous hardware platforms. Improve data service availability. We'll go over the differences between fault tolerance and high availability. We draw a very distinct line between the two here at Data Core. And we're going to explore how that's achieved in today's world. Improve data access performance. So by adding this additional layer of intelligence, the last thing that we would want to do is to slow down the access when the whole point today is to continually get faster and faster data access, at the same time also dealing with massive capacity requirements in the field. Pool storage resources, i.e. capacity management and added efficiency. Automate core storage functions, for instance, data protection. Expose programming interfaces and APIs. And allow modification of the storage architecture without interrupting the production workloads. So how does software-defined storage fall with regards to its place in the environment as well as any dependencies that it relies upon? Well, this is pretty straightforward and pretty simple. Software-defined storage relies on the concept of virtualization. Virtualization in and of itself does not completely define software-defined storage, but software-defined storage relies on the concept of virtualization. And of course, virtualization in turn relies on this concept of abstraction, which the industry is fairly well aware of today with server virtualization being around for as long as it has. The concept of abstraction is very readily apparent in that type of environment. We're going to see the same concept in the software-defined storage arena as well. So let's go through what abstraction is in a general sense so we can get appreciation for what software-defined storage is doing for us at the upper layer. So what's abstraction? Hardware abstraction in general sense, and by the way, it's achieved through software, serves to hide differences that may exist between the underlying hardware and the software that lives above it. People in the audience that have worked with Windows is, I'm sure, very familiar with the hardware abstraction layer, the HAL, within the Windows operating system, and that's precisely what we're talking about here. The purpose of abstraction is to simplify software development. So if we were in a world with all these various makes and models, it would be a terrible reality to have to recompile and reprogram the operating system for each make and model of the hardware vendor's platform. That would be extremely time-consuming, costly, and would not be received favorably in this fast-paced world that we live in today. So the abstraction layer translates generalized software functions into platform-specific hardware functions and vice versa. So what this allows us to do now is it allows us to have a much broader range of hardware support without having to make many, if at all, modifications to the software that rides on that hardware. So graphically, this is what it looks like. And of course, this is a server abstraction example. Those who are familiar with VMware, Hyper-V, Citrix, XenServer, or any of the other hypervisors that are out in the field today, this model generally applies to all of them. As you can see in the lower blue portion, we have the physical hardware abstraction layer, which again is a piece of software that translates between the underlying hardware and anything that rides above it. Now, in this particular case, I'm using terminology that's specific to VMware, but this can apply across the board. The virtualization layer is actually shown on here as well. So the hardware abstraction layer, of course, has to be first against the hardware. But then the next layer above that is actually where the virtualization, the scheduler, the memory allocation drivers exist to actually drive the hardware that's there and to do resource scheduling, which is the most important component of the hypervisor, to be able to time slice access to all those hardware resources for any virtual machines that we're running above it, as we can see here, operating system 1 or operating system 2 or 3 or however many systems that you have. So this concept is very similar as we transition into a storage abstraction example. Now this particular diagram is quite interesting because what we're actually seeing here is, again, the same layers of abstraction, but now we're talking about a storage virtualization layer, if you will, or a hypervisor, some people can refer to that as, but more strict to the definition, the storage virtualization layer, which of course now is only concerned with looking at the physical storage resources that it has visibility to be able to manipulate those resources and to be able to present those resources to the application servers that exist outside of this particular system. Now, the reason why I say this is interesting is because in this diagram, this can both apply to external storage arrays, as in the case of physical storage platform number 1 or number 2 next to it, or it could be internal resources to the server itself. And this concept is being seen a lot in the industry as of late as virtual SAN. And that's where we actually are able to leverage the local disk resources inside the server and then loop those resources back to the applications that are running, whether it be a localized application or whether it be an application that runs inside of a VM on that same physical host. But that keeps the accessibility of those storage resources very close to the server hardware, which of course has advantages of cost, performance, consolidation, and so on. So why is this important? Well, without the abstraction component, like we said, we're going to be very, very dependent on what happens at the hardware layer to then translate into the software layer. So without the abstraction, we're extremely coupled to the hardware platform itself, which makes life very difficult. So if we remain tightly coupled to that hardware, the benefits of software-defined storage are essentially lost. Or in this case, you can boil it down to perhaps being locked into a particular frame of storage, which of course lives within the refresh cycle of most storage platforms, which is 3 to 5 years. You'll be buying it all over again every 3 to 5 years. So that's really not a very, very cost-effective way to accomplish this type of software-defined storage goal. So it's much more effective to buy the intelligence once, the storage intelligence that drives all of those enterprise features, snapshots, CDP, thin provisioning, auto-tiering, and so on. Do that one time, and then simply swap out the physical disk resources as appropriate based on the storage task that you have in the environment. So let's take a look at a software platform that accomplishes this. Clearly, DataCore software, as everyone I'm sure is aware, has SANsymphony-V. The latest announcement with SANsymphony-V 10 brings all of these enterprise features together in a single solution to accelerate, centralize, and automate, pool, and protect all of the resources. So as you can see here on this very simple block diagram, we have, of course, the application server resources on top, the virtual machines, the physical servers out in the field, and then any virtual desktops that may be running. DataCore unified storage functions in the middle, and then, of course, the physical disk resources behind that, which, of course, we have exclusive access to. The application servers talk through DataCore. We provide all of the enterprise features that you would find in all the single frame and silo-based storage systems today, except that it's not tied to the hardware, and that's very key. So the back-end disks here in this diagram can be any block-level device that you have from any manufacturer. As long as we're able to see that storage, we can consume it and present it as virtual disks to the application servers above it. So a couple of simple use cases, right, where this is actually deployed. And again, the software-defined storage concept is deployed where if you want to virtualize existing storage hardware, clearly there's environments where the storage hardware is being transitioned in and out very rapidly. We're starting to see now in the field where customer environments are well above 1 petabyte of storage, but that's made up of 6 or 7 different types of storage technology, vendors, makes, and models. It's all over the map. So the ability to be able to unify that and virtualize that under one management front end, one storage engine, if you will, is very key. This concept of virtual SANs, a relatively new concept, again, moving the accessibility of the storage and all the storage services closest to the actual server that's running the application workload. And of course, flash, right? I mean, every single day you turn on the IT news, there's some news somewhere about flash acceleration, SSD, which are generally used to be synonymous, as well as additional capacities. I believe they just released, now a vendor out there released a 4 terabyte flash disk, which is tremendous. But you have all these different flavors of flash. Flash doesn't just, of course, apply to one type. There's about 6 or 7 that I could name with regards to different manufacturing processes, different ways to connect it, places where it sits in relationship to the CPU, whether it's in the PCI slot or in an array or somewhere else in between. So there's many different deployment models, many different types of flash. And the good thing is that as long as we can see that disk, we can leverage it no matter where it is in that stack. So here is a top-down view of what this would potentially look like. I think this is a little bit more detailed diagram than what we had just previously seen. So here's the fundamentals of what we do here. Running on any x86 64-bit modern server architecture today, your choice, IBM, HP, Dell, or whatever the case is. A common set of storage services for all storage devices. Again, regardless of what type of storage it is, magnetic disk, flash, whether it's PCIe-based connectivity, DAS, external array, fiber channel, iSCSI, all the above, doesn't matter to us. Common storage services for all those connectivity and device models, as well as pooling that into a centralized pool in order to better manage those resources and also to make it look and appear to the upper layers as if it's a homogeneous storage platform, but with many different performance characteristics. Take unlike storage systems, communicate seamlessly, reducing complexity and preventing downtime. One of the hallmarks of SANsymphony since day one has been the ability to not only accelerate workloads and to unify that storage, but also to prevent downtime through synchronous mirroring. And that has been a feature that has been around for 16 years now in our portfolio. And of course, replicating data, whether that be synchronous replication, or mirroring as we call it, or asynchronous replication, long distance, perhaps in a different state or a different country or a completely different part of the world. The ability to have the data in multiple locations removes the single point of failure in the architecture. Okay, a couple different ways, since Flash is such a hot topic right now, a couple different deployment models of where you might be able to use Flash. Of course, we talked about virtual SAN, and again, keeping those storage resources as close as possible to the applications themselves. Again, flash cards inside the data core node itself. If you have other storage devices that are external to us, such as other storage frames, storage arrays, again, iSCSI, fiber channel, what have you. And then, of course, the storage pools consisting of flash arrays, which are probably one of the more common deployment models that we see, because flash disks are very easily installed inside of existing arrays. 3.5-inch drives, 2.5-inch drives, lots of different configurations, lots of capacity capabilities within the chassis itself. Most times the arrays aren't purchased and installed day one that are fully loaded. So it gives the ability to be able to add various types of flash and other spinning disk type technologies to that existing platform, which of course can be easily consumed by SANsymphony. So let's go over a couple real-world examples of where we would see software-defined storage in action. So, common problem. Environment A has been in service for 2 years. The IT director has been given a project, requires many different classes of performance to be added for test dev. It might be for application, developing a new application in-house. It might be for M&A activity, acquiring a new company. We have to onboard all these additional folks, which of course consume resources on the network. And we have to be able to accommodate all these different types of new workloads that are introduced into the environment. So normally this would require significant preparation planning, workload calculations, ROIs for the CFO, and of course a lot of time to test and implement. So thankfully, the organization already had a software-defined storage solution in place. So the idea there is that, again, any block-level storage that we're able to see in the environment, we're able to seamlessly integrate into what we call our disk pools. And we can do that on the fly with no interruption to the production workload, because it all happens behind the scenes. And this idea of auto-tiering, which again is a very, very popular feature, maximizes whatever disk you put in that pool. So a perfect example of that would be if you ever had to add flash to an environment. Of course, you can add a little bit of flash, or you can add a lot of flash. Of course, flash is expensive, certainly more expensive than spinning disk is today. And the idea around auto-tiering is the ability to laser focus in on a particular data set. So for instance, we see in the industry about 10% of the data sets today requiring those high-intensity disks, those high-performance disks with high-intensity workloads. Of course, that number varies, but 10% is a good average number to speak to here. So that means that it would be senseless then to go out and replace your entire environment with flash. The economics alone could be prohibitive. But when you're only going to get a 10% return, because that is really the data set that requires that level of high-speed disk, and the other 90% is sitting there dormant or not nearly as active, or certainly not requiring that level of performance at the disk level, you're not getting as much bang for your buck on the return. So the idea around auto-tiering is that it happens completely automatic, as the name implies. It's in real time, and it's going to maximize the use of whatever that top-end storage is that you put in your environment automatically in the background for the workload as it demands it. So as workloads change, which of course is a complete moving target all the time, you couldn't possibly be making changes as fast as workloads change on the infrastructure. But the software is able to do that automatically in real time to be able to make adjustments as those workloads change and maximize the return on your investment for that flash or whatever the high-performance disk is that you have in there. And I say that because today it's flash. Yesterday it was 15K. Today it's flash. Tomorrow it could be something else. Again, as long as we can see that disk, we can leverage it in the pool. And of course, we touched on this already, but the idea around being able to protect that business-critical, mission-critical data through synchronous mirroring. Now, fault tolerance is one level of protection that you would always expect to have in a production environment, and that's what I mean by that is redundant controllers, redundant power supplies, what have you. But synchronous mirroring takes it one step further by adding a data level redundancy on top of the component level redundancy, which should already be in place. And we deliver a true highly available solution. And by that I mean when we present volumes out of the storage system to the application servers, we're presenting all of the volumes, all the LUNs, to all of the application servers over all the channels simultaneously. And in the case of synchronous mirror, we've got two SANsymphony nodes, so we're doing that across both of those simultaneously. So in our world, there's no concept of a failover because the volume is on server 2 just as easily as it is on server 1, and it does it simultaneously. So we're able to receive I/O from all channels through all of the SANsymphony nodes involved. In this case, we're talking about a mirror, so we're talking about 2. And if there was any sort of downtime, whether that be unplanned or planned maintenance, whatever the case is, the application servers simply see a change in the number of paths, but they don't have to wait for anything to happen on the storage system because all the volumes are presented equally in read-write mode fully on both sides. So that makes application servers very happy. So let's look at another problem, somewhat in reverse. Environment B. Now this is an environment that's been around for quite a long time. In fact, it's approaching what vendors would call the end of support life. So now IT director is faced with a hardware refresh. And I'm sure there's many people on this call that have experienced this. So now we've got to make a move. One way or the other, we've got to do something. We've got to purchase gear from the existing vendor. We've got to find a new vendor. We've got to augment in some way, but we've got to do something in a relatively short amount of time. So now significant effort has to be focused on choosing the hardware, the vendor, the technology, the features, the price, get it all done, all the due diligence, everything that goes into transforming an entire storage platform, which again, typically every 3 to 5 years. In this case, we're looking at a 5-year shelf life for this particular example. Oh, and by the way, we have 50 terabytes of production data spanning 100 volumes that have to also be migrated. Once all this is in place, we have to now spend time migrating this and without impacting production access to the data. Definitely a daunting task, but there is a solution. This organization, of course, already had some sort of software-defined storage in place, which makes this a lot easier than what it would normally be. So once the vendor's been chosen and the make and model has been determined and everything is rolled out, you literally simply add the new disks from the new chassis or the new frame, whatever it is, to the existing storage pool, and you remove the old storage volumes from the old storage array or the storage frame from the pool, and the software does all the migration work in the background, all while still serving up production access to the applications above it. Automatically migrate, no need to do anything else other than introduce the new storage into the pool, remove the old storage. In the action of removing those disks, by the way, some of the mechanics of how this works, of course, when you add the storage, we prepare the storage for use in the pool. But when you remove the storage, what has to happen first, of course, is we need to see which blocks are in use so that we can transition that over to the new storage arrays. And then only once the data has been moved off the old storage arrays is that old storage then decommissioned out of the pool, and then of course at that point you can turn it off and repurpose it for something else. But that actually goes into the next topic that we're going to talk about. But all this can be done with no interruption to production, and the data migration, which may have taken months, can be done in a fraction of that time. But there's something else to consider. The idea, of course, once you decommission storage arrays or storage frames, which, if you think back to when you purchased them, were fairly expensive, I'm sure. It's not uncommon to see a storage acquisition cost several hundreds of thousands, if not millions of dollars today, especially with the types of capacities that we're dealing with in the industry. They're becoming quite commonplace, 1 petabyte and higher. So that doesn't mean that just because the end of support life has been reached that it has to be completely thrown out. And I'm thinking that the CFO probably wouldn't appreciate that if he found that out. So what can we do? Well, still continue to leverage it. Because within a disk pool, the concept of auto-tiering, and in our case, it allows you to have up to 15 different tiers within your pool. Leverage it as a different tier of storage. It may not be a production tier, but you can certainly use it for test dev, VDI, backups, staging, archival. I mean, there's a whole myriad of reasons to still continue to use that disk in some way, because more than likely, as we've seen recently from a major storage manufacturer decommissioned a major line of their storage at the end of March, I believe, the storage is still very, very useful. Now, it may be a little more challenging to get replacement parts for it, but then, again, you have to cross that bridge when you come to it. But as far as the usability of that storage and extending the life of that storage, this platform will allow you to do that and repurpose it for other uses that may not be production grade, but still very necessary in the environment. And you can still squeeze a little bit more useful life out of that chassis or that frame before you are forced to have to literally fully decommission it for life. So this is just a repeat of what I just went through. And auto-tiering, by the way, that's really another key piece. Again, auto-tiering is a feature that exists within the disk pool itself. Imagine taking a storage frame that you might have paid $500,000 for. Pretty easy to accomplish that today with the capacities that we're dealing with. 3 or 4 or 5 years goes by very quickly. But let's say that, for instance, that at the time when you purchased it, you didn't have the ability to integrate flash, but now you can, because now the flash, or whatever type of flash or SSD type technology that's out currently, can be married alongside of that existing storage array, which by itself didn't have that capability, but now that it's in a pool that does, it looks as if to the application servers that that array has those characteristics, and the performance is greatly increased because of the shared resources within the disk pool. A pretty nice solution. So at this point, we're going to go ahead and turn over to some of the questions that we received during this presentation. I thank you for your time. Hopefully we didn't overshoot our time too much. So I'm going to read off a couple of the questions here that we have in the question box. So one of the questions, a very good question, is NAS at the back end supported or in the roadmap? So as of right now, NAS is not something that we can leverage because we leverage block level storage. NAS adds in an additional layer of intelligence that we're not going to be able to address, but the flip side of that, as you can see on this screen here that I have up, is that at the very bottom, in the bottom right-hand corner, you'll see that we have a NAS-SAN unified storage option. Well, keep in mind, we run on Windows. So therefore, we can, of course, leverage the services such as CIFS or NFS or the combination of the two because that already exists on that device. So we, in essence, can become both simultaneously your NAS and your SAN out of the same device, and that's what we refer to as a unified storage. And I don't believe there are any plans at this point to be able to consume any sort of NAS or CIFS type storage that I'm aware of because of that feature. Very good question. Would it be possible to get a PDF copy of the slides? Yeah, that's not a problem at all. We can, I guess we'll get all the emails for all the registrations that have taken place for this webinar, and we'll be able to send this over to you in short order. Another question, one more question I think we've got time for, is since we sit in the middle, do we slow down the accessibility to the data? And that's a very good question, a very common question that we get asked. Of course, the answer to that is no. In fact, we do the opposite. Well, we not only don't slow down access to the data, we in fact speed it up significantly. In fact, a very conservative number is 3 to 5x return by having us in line with the actual storage array. So a 300 to 500% increase, and that's a conservative number. Many customers have seen upwards to 10x because of our unique use of our high-speed caching and the algorithms that are associated with that. So we actually, our high-speed cache is a speed matching buffer. So we're able to get the data off the line as quickly as possible to free up the application server to continue processing or to continue sending I/O to us. And then we're able to leverage that cache, or in what we actually refer to as a mega cache, because you can put terabytes of RAM in these servers today. The more cache you have, the more data you can store in cache, in high-speed cache, the more likely that you're going to be able to hit the data that's already there in the high-speed cache without having to go all the way back to the disk. So that's clearly where you can see where we speed up the application significantly. So I think that's all we have time for today. I want to thank everybody for attending, and if there's any additional questions that we didn't have time to get to, we will certainly follow up with this after the webinar, and we'll make sure to get these slides out to those who have asked for it. Thank you very much, and have a great day.